So in this extension video lesson, we're going to look at the graph of the tangent function. And we're going to do kind of the same thing we did with sine and cosine. We're going to think through the unit circle, plot some points, and then make a sketch between them. Let's first take a moment to remind ourselves what tangent is. We'll just imagine a first quadrant angle here. So there's my theta. We already know that this ordered pair xy is the cosine of the angle, and the sine of the angle as the x and as the y coordinates. So tangent isn't a coordinate on the unit circle, but it's also not super hard to find. Remember what tangent is? It's opposite over adjacent. So in this case, that means that I want the y coordinate divided by the x coordinate of this point on the unit circle, which leads to an important, we call it an identity, a quotient identity. The tangent of an angle is always equal to the sine of that angle, because that's what the y coordinate on the unit circle is the sine of the angle, divided by the cosine of the angle. So with this idea in hand, we are going to see what a tangent graph looks like. Let's start by labeling some important points here on the unit circle. We've got 1, 0. We've got 0, 1. Back here is -1, 0. And then down here is 0, -1. Now, sine over cosine y over x means that at these nice angles, so 0, 90 degrees, 180, 270, 360, we can just take these ones and zeros and divide them. So let's do that. Starting with y over x at 0 degrees. Well, that's 0 divided by 1, which is just 0. So here we go. There it is. Next up, if we go now to 90 degrees, notice this time, y over x is 1 over 0. Division by 0, my friends, does not work, will not ever work. This is undefined. The tangent graph is different than sine and cosine in that the tangent graph is not continuous. It's got breaks in it. Because at 90 degrees, for example, it's going to show up as a vertical asymptote. There is no tangent value at 90 degrees. Let's continue on. At 180 degrees, once again, it's y over x, 0 divided by -1, that's 0 again. And at 270 degrees, -1 divided by 0, we have the same problem. We're going to have another vertical asymptote. Same is going to be true in reverse. So -90 degrees is that same vertical asymptote. -180 degrees is 0 again. And then -270 degrees puts us right here. That again is going to be a vertical asymptote. So right now, we don't really have enough information to get a good sense of how this graph looks. Let's put in a couple more angles. Now I've marked out here every 45 degrees. And the reason for that is this. In a 45-degree right triangle, the opposite and adjacent sides are the same. It's just half a square, basically. So up and down, side to side, same number. So opposite over adjacent is going to be, in the first quadrant, the same number divided by itself, so +1. So at 45 degrees, the tangent of 45 degrees is the number 1. Now you got to be a little bit careful as you look at the other quadrants because you got to keep your positives and negatives straight. So if we go 45 degrees, 90 degrees, and then over here to 135 degrees. Now the coordinates on the unit circle are actually negative square root of 2 over 2, square root of 2 over 2. It doesn't particularly matter right now. What it matters is that that's the same number with one positive version and one negative version. So when you divide them, you get a -1. So the tangent of 135 degrees is just the number -1. In the third quadrant, you're going to have the negative version of this number twice. The negative divided by the negative takes you back to positive. So in quadrant 3, your tangent's back to +1. So we see here a little bit of a pattern. And in quadrant 4, if you continue on to 270 to 315 degrees, which is off our scale, but over here, you'd have a positive x and a negative y. You'd be at -1 again. So this pattern does repeat itself in each of our, they're called periods. So each time a graph repeats itself, you call that a period of the graph. Now here's where I'm going to ask you now to trust me a little bit. We're going to focus just on this middle part. It does repeat in these other portions, but we'll pay attention to this one and then just kind of copy the shape over. The question then is, well, what does it do in between these points that we plotted? Does it go up slowly? Does it go up quickly? What does it do? So let's start by saying here, okay, if I imagine going from 0 degrees to 45 degrees, as I move to the side here around, notice we're moving up more quickly at the start than we are moving left. That means that the top is a little bit bigger than the bottom is in terms of its rate of change. It means we're going up pretty quickly. Once we get, though, over here, my top number, so as I imagine rotating around here, these last 45 degrees, the y value isn't changing very much, but the bottom value, the x, is getting very small. So you end up dividing by smaller numbers, smaller numbers, smaller numbers, smaller number. That makes your outputs, your tangents, go up really fast. So it looks something like this. In the other direction, it's kind of a mirror image. And this, my friends, is what a period of a tangent graph looks like. A little bit up like this, whoop, and a little bit down like this, whoop. It repeats itself over and over and over again. Now, over here on the radian grid, nothing changes. It's the same graph, except now you have zeros at every multiple of pi. So 180 degrees, pi radian. Negative 180 degrees, negative pi radian. At your 90 and your 270, that's going to be pi over 2 and 3 pi over 2. That's where you have your vertical asymptotes. 3 pi over 2. Same thing at negative pi over 2 and negative 3 pi over 2. And then 45 degrees, well, that's pi over 4. Negative 45 degrees, negative pi over 4. So we've got the same graph occurring, just on a different scale. And it's going to follow that same shape. So vertical asymptote kind of goes to about 45 degrees here in the middle, and then vertical asymptote again, up forever. Ooh, not my best tangent graph. Here, do a little bit of the same thing. Not sure why you're not doing what I want you to do. Ooh, so far my red graph is a lot better. Like this, and then over and up. And there you have it, your tangent graph. Now here's where I'm going to be very grateful that we live in the 21st century and not the 17th. Desmos makes a much better tangent graph than we're ever going to be able to make by hand. Notice it shows what we see here. We've got that kind of upward shape that repeats itself. They're vertical asymptotes every pi over 2 radian. I take that back. At multiples of odd multiples, rather. It's like a pi over 2, a 3 pi over 2, 5 pi over 2, 7 pi over 2. That would be on the unit circle when you're on the y-axis. You've got x-intercepts whenever on the unit circle you are on the x-axis. So those are your whole multiples of pi. Take a look at all that. Now, I want you to see the relationship between the tangent graph and the sine and the cosine if you put them on all at once. Notice that the red graph is sine. So when the red graph is 0, that means the numerator of your tangent function is 0. So the tangent graph is 0 as well. The red and orange graphs, the sine and the tangent, they have x-intercepts at the same places. That's always going to happen. Notice that when the blue graph, when the cosine graph is 0, that means in your tangent fraction, sine over cosine, you're dividing by a 0, which is what causes a vertical asymptote. So everywhere that blue graph has its x-intercepts, you'll notice the orange graph, the tangent graph, has that vertical asymptote occurring. This is one of those things where the more you look at this, the more you think about it, the more comfortable you will get. So I encourage you to look at it and think about it as much as you like.